This is the third installment in the first video relating to light and the Bohr model. In this episode we will be looking at how Bohr put together his model as well as the details of the structure according to Bohr. So the Bohr model takes from Rutherford and then adds to it. It actually clarifies some things that Rutherford had in his model that did not work. But the first of these is from Rutherford. The atom consists of a positively charged nucleus that's very dense, located in the center of the atom. Electrons are found in areas outside the nucleus in places called energy levels. And the electrons, this is a difference from Bohr, the electrons can only exist in specific energy levels, specific spaces. They can't exist in between, and electrons are only allowed, therefore, to have very specific energies. So if we look at, just as an example, if we're looking at Rutherford's model, and we've got a positively charged nucleus, and then we have electrons out here, it looks like we have orbits like Bohr is talking about. But according to Rutherford, an electron could exist anywhere in this space. Okay, so it could exist actually in this line or in this orbit, but it could also exist here or here or here. According to Bohr, the electron surrounding this positively charged nucleus, an electron could be allowed here, it would be allowed here, and it could be allowed out here, but not in between. So no here, no here, and no here. So he limited where electrons could be located. That limitation is what we would call quantized. See if I can spell this right. Q-U-A-N-T-I-Z-E-D. Quantized, which means specific amounts of energy. No other energies would be allowed. Two different states of the electron. One of them would be the ground state, and this would be the energy level of lowest potential energy. So the electrons that are in ground state are as low in energy as they can possibly be, while those in a non-ground state or excited state would be, the electron would be at areas of higher energy or higher potential energy, somewhere above their lowest state. Now, the energy level term is a term that came from Bohr as well. So when we say they're allowed in energy levels with specific energies, that is a result of Bohr. So each of these rings, each of these orbits is called an energy level. So this would be energy level, let me change ink colors here. This, for instance, would be energy level 1. This would be energy level 2, energy level 3, 4, 5, and so forth. So when we look at Rutherford's model, there were no specific energy levels. The electron could be anywhere from here to here, and actually out further than this as well. Electrons are allowed to transition. Transitions is when an electron can move between energy levels from low to high or high to low by going through some sort of energy change. So for instance, an electron can move from a low energy level to a high energy level by absorbing a specific amount of energy. That amount of energy, which we'll call delta E, or delta, which means the change in energy of the electron, is equal to the final energy level minus the initial energy level. Bohr also made this related to Max Planck's equation. This amount of energy, delta E, he said was equal to h times f, where h is Planck's constant and f is a frequency. So the change in energy is related to a frequency of light. An electron can also fall or transition from high to low energy level by giving off energy. And that energy amount is equal to the difference between the energy levels that were involved. Again, electrons lower their energy by emitting photons. This is an important statement. This is new. Electrons lower their energy by emitting photons. Okay, so that's unique. Electrons, as subatomic particles, lower their amount of energy, their total amount of energy, and in doing so, they emit photons. A photon is or also known as quanta, is a quantum of light. And that emitted photon is going to be equal to its energy is equal to HF. So suppose we have an electron in hydrogen and it undergoes a transition. It goes from 1 to 3. So if I've got my nucleus here and then I've got energy level 1, energy level 2, I'm just going to draw partial circles here because of space. Energy level 3, energy level 4, energy level 5, and so forth. This actually goes as high as energy level 7. So if we have an electron that goes through a transition from energy level 1 energy level 1e, that electron jumps out to energy level 3 and now exists here. To do that, it had to increase its energy because the lower the energy level number, the lower the energy of the electron. So the closer the electron gets to the nucleus, the less energy it has. So we have an electron that's going to jump from energy level 1 to energy level 3. So its energy is actually higher out here than it was originally. If the electron then falls back, which it should, as it does that, it's going to emit some energy. So this is an increase, and this is a decrease. The decrease is going to show a photon of light coming out of a specific nature. I'm not going to say color because we don't know if it's even visible light. So the electron then falls from 3 back to 1. It emits the same amount of energy that it absorbed. So this is very analogous to taking a baseball and throwing it up in the air and then letting it fall back down. The amount of energy, potential energy that it gains as the ball rises is equal to the amount it loses as it falls back down to its original level. This is called the conservation of energy. This is not a new concept for us. We know that energy is conserved and mass is conserved. So whatever energy is put in, so energy in on this side, energy out on this side in the form of a photon. And these two amounts, the energy in has to equal the energy out. So how does that relate to the absorption and emission spectrum of atoms? Well, let's say that we have let's start with this one down here. We have a light bulb and we're irradiating a cold gas with light from the light bulb. You'll notice that as it absorbs that light, and we have to think about what's absorbing the light, we end up with dark lines, okay, of very specific colors. When we think about what's absorbing, it's actually electrons, according to Bohr, absorb energy. And the specific energies that are absorbed correspond to frequencies and wavelengths that match these colors. So there's an amount of energy that's absorbed in the visible spectrum that would equal this reddish orange color here, this yellow here, green, and so forth. Then, if we allow this gas to heat up to the point that it's glowing and it's emitting light in exactly the same frequencies. So this is, again, electrons emit. So the electrons of this gas can absorb very specific energies, and they can also emit very specific energies, and those energies happen to correspond perfectly. So whatever the electrons can absorb is the same thing that they can emit when they're glowing. So Bohr didn't just make this observation. He was a mathematical physicist, and he derived an equation that related wavelength of energy absorbed to the energy level transition that the electron went through. This is the equation. 1 over wavelength, or the reciprocal of wavelength, is equal to a constant multiplied by 1 over nf squared minus 1 over ni squared, where n equals the energy level number. It's actually something called the principal principal quantum number. And of course this is going to be a final energy level and an initial, so we're going to have, in other words, a jump from the initial energy level to the final. And whatever jump we have corresponds to a wavelength of light. Now we're not going to do any actual calculations with this particular equation in this course. Just note that Bohr was able to derive an equation relating the wavelength of light to the energy levels that the electrons are moving in between. And there was a very definite relationship. He explained the visible spectrum. Okay, the visible spectrum was first seen by Johann Balmer, and this visible spectrum means all visible light emitted or absorbed. Okay? And this visible spectrum, he found, always involved transition electron transitions from an energy level n greater than 2 down to an energy level equal to 2. So whenever an electron transitions from a high energy level above 2 down to energy level 2, visible light is emitted. And likewise, if we wanted an absorbed light, if we had visible light absorbed, it was going to be an electron that was in energy level 2 being bumped up to an energy level that's higher than energy level 2. He was also, so he predicted this was already known at the time, been known since the mid to late 1800s, but he also predicted some spectral lines that had never been seen before. The Lyman series, so the ultraviolet range, predicted that they would be discovered, later discovered by Lyman. The Paschen series, which is in the infrared, predicted by Bohr, later found by Paschen. Okay, so these were predicted and found after prediction. So that's a pretty good support for your model, is if your model can make predictions about things and then you go look for these things and you find them, that's pretty good evidence that you're on the right track. Okay? So here's the idea. If we've got this Bohr atom and we have transitions, let's say from energy level, this is energy level 7 to 3 6 to 3, 5 to 3, or 4 to 3, this is all going to show up as infrared light, and it's known as the Paschen series. If we have any transition higher than 2 down to 2, we get visible series, and for the Lyman series, we get anything that's higher than 1 down to 1. Okay, so if we go back to this slide for just a moment, this particular one, the Lyman series, is from n greater than 1 to n equals 1. So an electron is going to jump from an energy level higher than 1 down to 1. This one is going to be n greater than 3 to n equals 3. So an electron at an energy level higher than energy level 3 falls to energy level 3, and in so doing gives out an infrared photon. There are other series. These are just 3 of the most famous, but there are other series of light. For instance, any energy level higher than 4 dropping to 4 would be another example. Okay, so there were some problems with Bohr's model, but one of the problems was not the light. He was actually able to perfectly predict these spectral lines. He was able to perfectly explain the Balmer spectrum or the Balmer series and make predictions about others, and his model worked very, very successfully. However, there were some problems. The biggest problems was this. Bohr's model worked well for hydrogen. 1 proton, 1 electron. It's the simplest atom. However, if we went to any atom with more than 1 electron, the model failed. Didn't work, didn't make predictions. So this is a pretty big problem when you consider that not at Bohr's time, but at this point we have 1 hydrogen, that's 1 element, and we have 117 elements not well described by Bohr. Okay? So his model was perfect for hydrogen, but after hydrogen it fell apart. But that does mean something must be good. If it works for hydrogen, then there must be something correct about it. But there's something missing, obviously, something significant that's missing, because we have 117 elements that it doesn't work well for. So some things that come from Bohr's model that we still keep. We have the explanation of line spectra still accepted. Even though his model doesn't necessarily always predict perfectly, we still say emission and absorption spectra due to electrons jumping. He also applied quantum theory to atomic structure for the first time, and since this was done, we've never gone in another direction. Electron energy is still viewed as quantized, and our modern model of the atom is still a quantum model. Now, another document that I want you to look at, you have reference tables that I've given you, and if you turn to the last page, you will see this diagram, and this might be rather important in terms of solving some problems. For instance, let's suppose we're interested in the type of light, the type of electromagnetic radiation produced when an electron transitions from n equals 3 to n equals 5. N equals, let's go 1. Okay, so we have to find n equals 3. Here's n equals 3, and this electron at this spot, we see it moving to n equals 1. Okay. And I'm not getting that to show up very well. N equals 3 to n equals 1. And 3 to 1. Then we follow the line backwards here, and we see that it's going to correspond to a wavelength. These are wavelengths. Wavelength of 103 nanometers. So that information's up here, and that falls into the ultraviolet range. So when an electron transitions from 3 to 1, follow the arrow, it's in the ultraviolet range. One of the other interesting points about Bohr's model is this. This actually presents a little bit of a problem that would have to be solved. We said that electrons could not be represented here. They couldn't exist in between energy level and energy level 1 and 2. They couldn't exist here. They could not exist there. So they could only exist actually in the orbits themselves, not in between. So the question would be, is if you got an electron transitioning, how does it get from this point to this point, or any 2 points going between energy levels, without passing through the space in between? So how can an electron get from energy level 2 to energy 1 and not pass through that physical space? Bohr developed the idea of quantum leaping. Quantum leap is when an electron disappears from one place and reappears somewhere else. That's difficult to imagine, and a lot of people, probably even Bohr, had an issue with it. The modern model actually explains how that happens. But quantum leaping, if you've ever heard that term, actually came out of Bohr's model. With that, we're going to end this first section on Bohr and light. Following this video, the next video down the line will move us into the modern model of the atom developed by Erwin Schrödinger.